Hey guys, Lauren here. So today I'm just going to be talking to you about sickle cell disease, which subsequently was my choice of genetic disease this semester. Um, we've been working on this for the past 8 weeks. We have delved really deep into each of our chosen diseases, and I'm very excited to see all of yours and see what you came up with over the semester. So, yeah, here's my final presentation on sickle cell disease for our Genetics of Health Professions class. All right, here we go. Oh, and I do want to preface also, I am coming down with some colds right now, um, that time of year, so I apologize if I'm all congested and nasally. But yes, so I apologize, just bear with me. Okay, so overall, I just wanted to talk about, what is sickle cell disease? So, what exactly is it that causes the genetic modification? So, as you can see in this picture here, this is a normal cell, and these are our normal hemoglobins, right? And in our sickle cell, you can see our abnormal hemoglobin here and abnormal shape of the cell. So, what happens here is the normal cells, they're free, they're nice and flat, they're free to pass through our blood vessels and without any trouble. But however, our sickle cells, for those who have them, are, sickled in a crescent-like shape. So they're very easily stuck together, very easily able to create blockages and stopping, oxygen getting through to your body, which is not good. This is not what we want. As, hemoglobin is what carries oxygen through our body, which I will go through in a second also. But so again, yes, people with this type of disorder have a modification where their red blood cells and the hemoglobin molecules are altered, creating the sickle cell shape and causing blockage and all these kinds of not good stuff. So, okay, so I just want to talk a little bit about what is hemoglobin. So, as I kind of mentioned, the reason that sickle cell disease is what it is it is the abnormal shape of hemoglobin in the red blood cell, causing it to be the sickle cell shape. So, I just wanted to kind of go over, what is a hemoglobin molecule? So, each hemoglobin we have, hemoglobin is in our red blood cell. So here we go. We have the red blood cell, and we're expanding out into our hemoglobin molecule. And so we have every hemoglobin molecule is created of 4 globular chains. So 2 alpha chains and 2 beta chains. And at the center of each chain, whether it be the alpha or the beta, is a central heme group. And attached to each heme group is an iron atom. And as I will talk more about that on the next slide, however, but I'll just preface it now, the oxygen binds to the iron atom. So as you can see, this little red ball, the oxygen binds to that iron atom per each hemoglobin molecule. So there's 4 iron atoms per each hemoglobin molecule because there's 1 iron atom per each heme group and then 1 oxygen per each iron atom. So for a total of 4 oxygens that can bind to each given heme group. And as we know, hemoglobin carries oxygen from our lungs to our tissues. And I will talk about cooperative binding on the next slide. A little more about that. Okay, so how does hemoglobin exactly bind to oxygen? I kind of just discussed it, but it binds directly to the central iron atom at each heme group. So talk a little bit about cooperative binding here. So cooperative binding is when the first primary oxygen that binds to the first heme group, or first iron atom, rather, per each heme group, makes it easier and more likely for other oxygens to bind to the other 3. So I like to think of this example. It's like, if you're in a new school, right, or in a new cafeteria or just some open space, you're less likely to sit at a table, right, in this cafeteria if there's no one sitting there, right? Like, you don't want to sit alone. So, but however, you're more likely to sit down if others are already sitting. So that's exactly essentially what cooperative binding here and what happens when oxygen binds to the hemoglobin is once the first oxygen binds to the first iron atom, it makes it easier for other oxygens to bind to the other subsequent iron atoms in the hemoglobin molecule per each heme group. So Once the first one sits down at the seat, it makes it more likely for the other ones to also sit down at the table. So again, it just makes it easier, just the structural, importance of hemoglobin and how it binds to oxygen. All right, so let's talk about some characteristics of sickle cell disease. So over here I have anemia, fatigue, delayed growth and development, shortness of breath, hypertensive issues, and extremity swelling. So again, oxygen is carried through our body, right, by our hemoglobin molecules. That is what transports oxygen through our body and gives it to our cells and from our lungs to our tissues. It's very important to carry that oxygen. And if our muscles and our organs don't get this oxygen, obviously bad things are going to happen. It's very important. It's the basis of our living. We need oxygen to survive. So I just have here this picture, the difference between some acute complications and some chronic ones. Some acute ones, stroke, meningitis, things that happen real fast, right? Like they come out of nowhere. Cholelithiasis, so gallstones, papillary necrosis, osteomyelitis, bone infection, acute chest syndrome, and glaucoma, stuff like that. It's never good. If whatever part of your body is not getting the oxygen it needs, things are going to go wrong. Some more chronic complications, anemia, leukocytosis, delayed puberty, as I mentioned, skin ulcers, avascular necrosis, cardiomegaly, so enlarged heart. Yeah, so none of it's good. Yes, none of it's good. We need oxygen to our body. So these characteristics of sickle cell disease, when someone has it, are no good. So that's why it needs to be managed and treated properly. So exactly where is it that, this mutation happens for someone to get sickle cell disease? So it happens on chromosome 11, specifically on the hemoglobin beta gene found on chromosome 11, and it is caused by a mutation in that gene. So I see here, right, we have our human chromosomes 1 through 22, and then our sex chromosomes X and Y, making us male or female. And then specifically right here on the hemoglobin beta gene of chromosome 11, the mutation of that is what causes sickle cell disease. Excuse me. All right. So what are some molecular causes of sickle cell disease? So we have hemoglobin, as I had mentioned, transports the oxygen to other parts of the body, to every part of the body, really. We need hemoglobin to transfer everything for us. And I did mention this already, but I'll go over it again. So, here we have a normal red blood cell carrying oxygen through the bloodstream. They're nice and flat. They flow freely. Here's our oxygen carrying through. This is normal. And here we have our sickled red blood cells. They clump together, they stick together, they clot, and this is not good, right? So because their shape causes, buildup of each other and pile up in blockages, damaging vital organs and tissues, which is never good. Obviously, we don't want to damage vital organs and tissues, so clearly the sickle cell disease is not good. The sickle cell shape is very bad, again, causing the blockages and damaging our vital organs and tissues. So, not good. So as we have learned throughout the entirety of this class, different modes of inheritance, specifically for sickle cell disease, it is autosomal recessive. So again, this just means that the offspring, in order to have the disease, needs to have one copy of the mutation from each parent. So here we need to have one copy of the mutated hemoglobin beta gene on our chromosome 11 that is sent from both the mother and the father of the offspring that would have sickle cell disease. So even if one of the parents is a carrier, obviously, they still can pass down that chance of sickle cell disease to their child, and they wouldn't show it, but they do have a mutated version of it. But they just don't have the two mutated forms to show the phenotype. So I'll talk a little bit more about this on the next slide also, but I liked this visual here, so I just wanted to mention it. So here we have our autosomal recessive mode of inheritance. So we have our carrier father, our carrier mother. Here we can see, since they're both carriers, they both have a mutated copy of the gene on our hemoglobin beta gene on chromosome 11. So we have a 25% chance that the son or daughter will be unaffected completely, a 50% chance that there will be a carrier, so they'll have a mutated version, but they will not show sickle cell disease, and then a 25% chance that the son or daughter will be affected with sickle cell disease. So here we go again. Just want to talk about this, show some Punnett squares here, and exactly how this is showing the probability of these. So I just have a few examples here. My first example, so our parent genotypes, we have SA and SA. So little preface here. So in order to have sickle cell disease, it is the S, right, that needs to be passed down from each parent to have sickle cell disease. So here we both have two, we have one S and one A. So the genotypes, S and A, the actual gene pattern, both phenotypes for this, however, would be normal because neither parent has two capital S's. So neither parent actively has sickle cell disease, but both are carriers. So we have two parent carriers. We have SA, SA. Here we have a 50% chance. Actually, this is the exact example from before. But we have a 50% chance that their child would have sickle cell disease, and then a 50% chance, a 25% chance, this should be an A here, my apologies, but a 25% chance that they won't be affected, and a 25% chance that they will have it. So again, yes, so not good, but all right. So my second example here, our genotypes are SS and SA, our phenotypes being the SS parent having the sickle cell phenotype and the SA having the normal phenotype. They wouldn't show it. So as you can see here, and again, I apologize, this should be an A. This should be SA here, but here we have, and this should also be SA. So here we have a 50% chance that they will have sickle cell disease, and a 50% chance that they will not, that they would just be carriers for it. So yes, more of a chance, actually 75% chance, rather. So, but anyways, so parent genotypes here, we have SS and AA. So as you can see here, from this hybrid cross, all children would be carriers. So we have our sickle cell phenotype for a parent, and then a normal phenotype for the parent, and one parent is not a carrier. So yes, as you can see here, this just kind of shows the inheritance pattern of autosomal recessive inheritance. All right, so is genetic testing available? The answer is yes. So doctors diagnose sickle cell through a blood test that checks for hemoglobin S, which, as I mentioned in the first slide, which is the defective form of hemoglobin that causes them to sickle. And screening programs for newborns are required. Recently, it has become required as, post-birth testing for newborns, that they are tested for sickle cell disease. And again, this early, I'll talk about this on the next slide, but this early detection is very important. As you can see from when I was talking about the complications of sickle cell disease and the characteristics, it's not good. It causes many, many health issues, both acute and chronic. So early detection is very important. But, so here we have unborn, so are there other genetic testing? Short answer, yes. Unborn fetal testing. So we have, the doctor takes a needle from the fluid of the unborn child while in the mother, so while still in the uterus, and this tests for sickle cell. And then we also have pre-implantation genetic diagnosis, which is used in conjunction with in vitro fertilization. So when you are, creating the embryo in a petri dish, and you can test for, the parents must be carriers for sickle cell disease, and you can test for this before fertilization. So before you do the in vitro. So again here, why mandatory testing on newborns? Briefly mentioned this, but I'll go over it again. So blockages and damages vital organs and tissues. We don't want this. We don't want that life for our children. So early detection is very important in order to prevent these blockages and damaging vital organs and tissues. And again, detect early for early management. If you can detect it early, you can manage it early. So again, it's my reference list. I hope you enjoyed my presentation. It was a pleasure working with you all semester.